Hey, what's up, YouTube? This is Dr. Schleith, and it is Pi Day 2025, which means it's the fifth anniversary of this YouTube channel. It is also Einstein's birthday, and as is the tradition on this channel, I always like to take a look at one of Einstein's papers. I think I've probably looked at this one before, but it's a great paper on a heuristic point of view concerning the production and transformation of light. It's the one paper that Einstein himself called revolutionary when he was writing a letter to his buddy Conrad Habicht talking about some how he finished his dissertation, how he wanted to read his, and it's a funny letter. Here he talks. The paper is really a good example of the nature of science too, because he talks about the wave theory of light, which operates with continuous spatial functions, has proved itself splendidly in describing purely optical phenomenon. So I'm reading from this paragraph down here. And will probably never be replaced by another theory. Okay, so he's sort of admitting, like, we know that light is a wave, but a heuristic, sort of a working hypothesis, sort of a way to move forward. Well, uh, the so-called ultraviolet catastrophe needed an explanation. There's a really good video made by Physics Girl talking about the ultraviolet catastrophe. I encourage you to watch that sort of led to these conclusions and indeed the birth of quantum mechanics. And I love when he says in this paragraph here, he says, in this paper, I wish to communicate my train of thought and present the facts that led me to this course in the hope that the point of view to be elaborated may prove of use to some researchers in their investigations. And so he's just sort of offering this, this train of thought as a way to move forward. What if light could also be a particle? And now we have this wave particle duality. And indeed, I think if we go maybe one or two more pages into the paper, we can see that there's pi showing up. The radiation may be considered as the most disordered process imaginable. And so here he's talking about Max Planck in a paper that he had written before. I also, on this Pi Day, wanted to share sort of a little bit more practical knowledge in the spirit of this channel, Ace Physics. And this is one of the labs that I would like to do sort of very early on in the year for students. And so it's a circle lab and certainly appropriate for Pi Day. So my students will recall that every Wednesday was lab day and we're collecting data and we're typically going to be plotting that data on a graph. And a circle lab is a great example of how there are relationships in nature that we can visualize by collecting data and plotting it. And so what we encourage students to do with the circle lab is to find circles in the classroom, and we want to try to measure the distance across the circle, which students will know as the diameter, and then the distance around that circle. And indeed, it should sort of make intuitive sense that if there's a small diameter, then there should be sort of a shorter distance to make it around. And if we have a larger diameter, well, then the distance around that circle, the circumference, is going to be longer. So there's intuitively there's a relationship between these things. And indeed, some clever students will sort of immediately recognize what that relationship is, the numerical sort of value, which is pi, right? So in other words, if we know how far across a circle is, d the diameter, we know that we can multiply that by pi, and that gives us the distance around the circumference. So the circumference of a circle is equal to the diameter times pi. So if we plot, let's see. So students will sort of think about, a line y equals mx from their math class. And so we think about this as the x-axis and this is the y-axis. And so what we kind of want to do is make this equation resemble sort of this here. And so we'd say, well, our slope is going to be our conclusion, pi, right? And so that's on the side of the equation with the diameter. And so we would plot the diameter. We want to get students sort of used to, metric. And so we probably plot this in centimeters for circles that you could find in the classroom, maybe meters. And then we plot the circumference on this side. And so we have sort of circumference equals pi times d. Y, which we're plotting the circumference on the y-axis, equals mx, which in this case, the slope will be pi. And so if you plot different diameters on the x-axis in centimeters, and if you plot the circumferences of those circles on the y-axis, you'll find that as the diameter increases, the circumference increases, just sort of like these circles that I drew over here. And if students do a really good job sort of plotting that and measuring the distance across a circle. So they might find a coin, or they might, the lid to, a bottle or something like that. You'll find various circles sort of around the classroom, or maybe you have to, venture out for a little field trip onto campus to find different circles. It's important that the circles are sort of within the same kind of range that you can plot it on the same graph, to scale. Measuring the distance around can be kind of tricky. So students can either do that by like putting a string around the circle and pulling it straight and measuring that, or sort of like, well, here's a circle right here. You can measure the distance across and sort of measure the, your fingertip to your thumb tip, and kind of, go like this and try to measure that, or maybe measure around a circle, with centimeters, and sort of place the ruler sort of going around it and sort of adding up all the centimeters or the tenths of centimeters, however precisely the students can be with that. And indeed, the more accurate they are in their data collection, the closer they'll get to the known value of what the slope should be, which is pi, right? So indeed, as these diameter values increase, so too will the circumferences, and students can find 2 points that are on their line of best fit. So once they've plotted, 6 or 7 different circles, then they're going to place their clear plastic ruler over their data points. They're going to try to sort of visualize the line of best fit, and they're going to commit to that line and draw a single straight line that represents the trend in the data. The moment they draw that trend line, that's more accurate than any individual data point. So we never want to calculate the slope by using data points. We'll have those points in our data table, and we could just plug them in, and what's the point of plotting? And if we're just going to use 2 data points to calculate the slope. So the key is to find points that intersect the gridding of your graph paper very neatly. And so if you have, really small squares on your graph paper, that's easier to do. But, any graph paper should work if you're spreading your data out far enough over the page, and you're going to try to find 2 points that, using your scaled axes, you can read off the coordinates, right? And so this would be, distance 1, circumference 1. And then this point up here would be, have a distance 2, and the y coordinate circumference 2. And then you could use the slope formula, right? The difference in the y values is the rise. The difference in the x values is the run. So students will think about, again, in math class, like y2 minus y1 over x2 minus x1, when we think about the horizontal axis is x and the vertical axis is y. But here they're actual things that we're measuring in nature. It's not abstract math, it's physics, and it's something real that we're measuring. So when we sort of apply this formula to this, it's going to look like what? It's going to be the difference in the vertical axis coordinates, so c2 minus c1, the difference in the circumferences, over the difference in the diameters, and that will be the rise over the run, which is the slope of the line. That slope, if the students did a good job, should be equal to what? Should be equal to pi, right? Because indeed, if the circumference equals pi times d, that's sort of what the theory suggests, then we can kind of prove that with some data. And so that's a really nice Pi Day lab. It's a great way to introduce students to data collection and sort of carefulness of measurements. And I think the most important takeaway is that there are relationships in nature which we can discover with science. Once we start applying things, say, wait a minute, there's a relationship between these things. And sometimes it's not always intuitive like it is with a circle. For example, a very famous graph that Edwin Hubble, plotted when he started looking at galaxies and how fast they were speeding away from us as a measurement of their redshift, how far their light had sort of shifted to the red end of the spectrum. And the galaxies that are the furthest away from us, so the ones that have the greatest distance, have the highest velocities. And so you wouldn't think that those things might be related, that how far a galaxy is from us determines how fast it's moving. But if we think about the universe as expanding, then that makes perfect sense. And so sometimes we discover these relationships in nature that aren't intuitive, and they lead to a groundbreaking discovery and an insight into the nature of the universe of which we are a part. Happy Pi Day, everybody. And this is Dr. Schleith. Obviously still living the physics life. We'll see you next time.